For those of you who are unfamiliar with our program, Astra is the newest initiative of the Australian Youth Aerospace Association, and it is really designed to be an 100% online program. So this is just the beginning, and you can join in from wherever you are. It's a 5-month program where participants will be given a profile or a character and asked to try and think about a complex space issue in the domain from the perspective of themselves, but also from the perspective of the profile they've been given. The program will include presentations, Q&As and feedback from our partners, including the South Australian Space Industry Centre, where our speaker, Darin Lovett, joins us from today. So Darin has been a supporter of Astra since it first began, since before it was even called Astra, I think. And so we're very, very grateful to him for joining us today. So I'll pass along to you, Darin.
Okay, thank you, Megan. And thanks very much for inviting me here today. I'm a real fan of everything you do, AYAA, but also about the new Astra initiative, and really commend anyone out there who hasn't seen what they're doing to look it up online and potentially join. It's mainly focused on Australia, and I do know we have an eclectic audience tonight. I was looking at some of the LinkedIn respondents. I counted over 30 countries, which I guess is a real sign of how COVID has changed the way we disseminate information, because in the past we would have done this in a room with 20 or 30 people. And so this is a real way to stretch and share information around the globe and around to people who need it. And now this brief is unashamedly focused on the basics of space, to try and bring together a multidisciplinary perspective for many of the students who are coming up and going to grow into this new space industry, which we hope will really be kicking off in Australia over the next few years, and it's certainly happening around the world. So I'm going to be talking for about 40 minutes, and then we'll have time for questions, but feel free to post them online. I think Megan's collecting them all, and we'll talk about them at the end. So as Megan said, I'm Darin Lovett. I'm the Director of Space for the South Australian Space Industry Centre. So that's a state government body. Don't represent the federal government, which is the Australian Space Agency, but we work very closely with them. And in fact, they're down the road in Adelaide. And at the end, if we have time, I can very happy to talk about what's happening in the local space community here in Adelaide and South Australia, but we'll really focus on the broad fundamentals first up. I'm just going to try and get my slides to work. Okay, so where have we come from? Look at what's happened in just 10 years. So the iPad was unveiled 10 years ago by Steve Jobs, and a short time after that, he used the same analogy he had used at that first unveiling, but sort of amplified it. And he said this quote, "It's in Apple's DNA that technology alone is not enough, that it's technology married with the liberal arts, married with the humanities, that yields us the result that makes our hearts sing." And if any of you have used an Apple product, you know that it's just not the technology, it's almost seamlessly integrated into beautiful objects of capability. And he had a point. We're looking at a new domain that is emerging in terms of what has typically been characterized by a technology focus. And so as we move into this new era, like the other domains that have developed technology and created capability, we really have to think about that multidisciplinary aspect. And what is it that people can bring to the table to help build and feel new capabilities with a different view to how things are working. Now, change is afoot. Thomas Kuhn, in his book, The Structure of Scientific Revolutions in 1962, coined the term paradigm shift. And he talked about a paradigm being one view of the world that inculcates technology, academia, government, and the whole way society sees something. His argument was that you can have all the technology in the world, but it isn't until you've undergone a paradigm shift that you've brought everyone over to the new paradigm that you can now use that new paradigm or worldview to solve new problems in a way that is unique. And that, in fact, once you've moved to that new paradigm, the old profession will have changed its way, and that its methods and its goals will have changed as well. And similarly, Clayton Christensen, who is an author of Disruption and talks about technology, argued that often the new paradigm will displace old markets in ways that are unseen. And so I'd argue that we're right now witnessing a paradigm shift for space. We are unaware of where some of the new markets might come from, but there is much potential out there to demonstrate and to make use of. Now, I am going to go back to this picture of Australia in 1967, but it's actually important from an international perspective because Woomera was the playground in 1967 for many nations. We had the Italians, Germans. I know there was someone from Belgium who was online, but so there were countries who were involved in the Woomera program. And a lot of people see this and go, hey, that's what space is. This is a space picture that shows, you know, very large objects moving into space, large platforms that you would have seen through NASA and Cape Canaveral. And it sort of typifies what most people consider as space. For Australia, this was a highlight. Australia was the 4th country in the world to put its own satellite up into orbit from its own soil. Admittedly, it was on a hybrid rocket with a first stage provided by the US Army as a Redstone rocket. But it was impressive from an Australian perspective. But really, for Australia, nothing much has happened since then in the last 50 years, since that ELDO program. So where does that take us? Now, space has undergone some shifts for Australia. Just a couple of months ago, 19th of September, we had a launch from Kaniba, a suborbital launch for Australia, with 2 space-capable rockets. They could have gone to 100 kilometers plus, but basically delivered 2 payloads up and re-entered, well, basically landed on a range, so Earth to Earth. But for Australia, this is really a huge jump forward because this was the first commercial launch we've had in 50 years. And so for us in South Australia, you know, really represents where things are going. And one of the things that we've identified is if we're to build this value chain for space, we really need all the elements of space. So it's not just building spacecraft. For nations to be competitive and on a global market, if you don't capture a lot of that upstream value chain in the same way that SpaceX has done it, then you're going to be outcompeted or outpriced by your competitors, even if you have a very compelling payload. So this is very good for Australia, very good for the world in terms of where things are going as new rockets are being developed. Now I'm going to cover a few things here. Where is space from a sort of pictorial perspective so you can visualize it? What do we get from space? And this is from the perspective of services. What does space give to us on Earth? Not talking about human spacecraft programs or exploration, more about the services to terra firma. What makes space unique? You know, what are those essential elements that make space what it is? And then finally, challenges and opportunities for Australia, but some of these will extend to our international attendees. So very briefly, work with me here, but I want you to picture the Earth as a globe. See the lady there in the bottom left, holding up a globe about 40 centimeters in diameter. The actual Earth is 6,500 kilometers in radius. So if you just do your maths, 20 centimeters over 6,400, you get factors of 800 in terms of the radius change. But what I'm trying to show here is if you do have this Earth, this small Earth holding up about the size of one basketball, then the Himalayas, which we consider very large, 8 kilometers over 6,400, 1/800th, is only 1/4 of a millimeter thick. So the Earth, from a space perspective, is quite flat. All of the dimples on the Earth, the mountains that we take for granted, we think is very high, is actually quite a small sliver and just a pimple on this planet. Moving a bit further, aircraft fly at about 13 kilometers, so 30 to 50,000 feet, and we're now only 3/4 of a millimeter above. So when we think of the air as this sort of third dimension, we often talk about that. From a space perspective, it's really, again, quite thin. We've got this onion skin of atmosphere that surrounds this fragile planet. And then looking further afield, this chap, Alan Eustace, jumped out of a balloon, jumped off a balloon. He was from Google, but Google didn't pay him. He got up to the tropopause and hit 41 kilometers. And you can just start seeing the curvature of the Earth here. So he's getting up high. Now we call space, we say it really starts at about 100 kilometers. Now we can go into the mechanics of this. Von Karman argued that if you have an object moving at speed, in order for it to fly, you need atoms and matter to flow over the wings to provide lift. And if you're going to fly and keep going up higher and higher, you need to go faster and faster because there's less air. And at some point, you're now going to be in orbital velocity. So the velocity needed to attain an orbit around the Earth. And that altitude happened to coincide with about 100 kilometers, quite neat. So often people, and this is often used in international definitions, space is considered to start at 100 kilometers. But for practical purposes, it doesn't really matter. It certainly matters legally, but really nothing is going to operate at 100 kilometers. You're too low in the atmosphere. If you're in orbit, you'll be dragged back in and you'll burn up. And you're too high for a plane because you can't maintain your lift. So it's a bit arbitrary, but it does demonstrate where things are going. Now, 100 kilometers is now about 0.3 or 0.75 of a centimeter. We're still talking very close to the Earth. So we've got this thin layer around the planet that we consider the third dimension. Now, the International Space Station, I'm sure some of you have tracked this as it flies overhead, anywhere from 300 to 400 kilometers. We're now 1 centimeter above the planet. So 1 centimeter above this planet, literally thousands of objects whizzing around the Earth every 90 minutes, moving at 26,000 kilometers, coalescing around either the poles or shooting around the equator. So there's a lot of stuff up there that's in what we call low Earth orbit. And then finally, if we're going to expand out to the sort of fairly distant region of space that we still operate a lot of satellites, the geostationary orbit, 36,000 kilometers away, we're now about a meter from this planet. So between that 1 centimeter and 1 meter, you've got 99% of that volume, trillions of cubic kilometers of space. It really is a large, large domain and very hard to conceive of distances and matter in that domain. But I'll talk about some of the specific regions in that area as we go through. So that's space in a nutshell. That's sort of where it is. Now, what do we get from space? So I'd argue that we only get 3 traditional services from space, and this hasn't changed since Arthur C. Clarke postulated that you could put objects into space and attain geostationary orbit, or other science fiction writers. The first is you can see from above. So we've always, through warfare and throughout history, tried to attain the high ground in the Civil War with balloons, in World War I with aircraft. And this picture of a captured V2 rocket taken from the Germans in 1947 over White Sands, New Mexico at 104 kilometers, where they cut a hole in the side of the rocket and slapped a camera in there and took the first image from space, 104 kilometers. So you can see that curvature of the Earth that really is starting to show, and demonstrably so, what it is that you get from space, this huge vantage. And that really fast-tracked the Cold War and the access to space. So the US and the then Soviet Union in a race for space, trying to put up satellites to see into each other's territory, because at that time you could gain overflight. And if you look at this shoot down of Gary Powers in his U-2, it basically forced the US into space, or to spend billions of dollars to attain the high ground there. And that picture just shows you one of the ways they did it. They put up wet film, so kilometers of what was considered old film stock, celluloid film, up into space, taking pictures over the USSR, deorbited in a capsule, which then popped out a parachute and floated to Earth, and then captured by this aircraft down here in the bottom right, in order to deliver pictures that you see in the bottom left, which helped de-escalate the Cold War. So a lot of money, a lot of effort, and you've got to remember this was all happening quite secretively in the US and the USSR at the time. So billions of dollars spent to really kick off this space race. Now, the second reason we go into space is to is to communicate. And so we have the idea that the Earth is round. Some of you may not think that so if you're part of the Flat Earth Society, but I can assure you it is. I've been up high and seen the curvature. It really is round, but the roundness, we often underestimate its effects. So the curvature of the Earth really limits our ability to project communications in terms of direct line, UHF or VHF. And so as an example, if you're on the Empire State Building, for example, you only get about 40 kilometers range till you hit the horizon. So if you want to get higher, you need to get up into space. And that's what NASA proposed in 1969, put a satellite up there, and now you've got your communications network bouncing signals around the Earth. Okay, and the third reason we go to space is to navigate. We've always navigated using the stars for thousands of years, tens of thousands of years. And now if you translate that to space, call it what you will, GPS, BeiDou, GLONASS, any of the other systems, the Indians have quite a novel system as well. We're talking about the ability to provide an artificial reference system in space. And these objects are at about 20,000 kilometers around the medium Earth orbit, and they provide that reference system. And now, as we know, it's ubiquitous. And GPS technology, which was originally developed for the Polaris missile program and nuclear submarines in order to provide updates to fix their computers before they went and did a potential strike, is now ubiquitous across society. And not only that, its capabilities permeate society to such an extent that we really don't understand the second and third order effects of how that interferes or interrelates with society in terms of timing, the ability to track objects, to provide just-in-time goods. And just think, as an example, when you have jamming, which has occurred in the Caspian Sea, and ships are unable to maneuver without GPS, then the second order effect might be that Lloyd's, that typically underwrites ships for insurance, refuses to underwrite those ships, and therefore the cargo isn't moved. So we've already seen with COVID, the fragile supply chain that we have around the Earth could potentially be affected by other things such as jamming these GPS signals, which are very weak. Okay, so that's what we get from space. Now, what makes space space? Now I'm going to talk about 10 things that sort of make, I think, the sort of quintessential elements that define space and make it what it is. If you're a strategist, some strategists will talk about the dimensions of strategy. You know, what is it that those essential elements that really characterize the domain or the place that you're looking at in order to really focus on the big picture ticket items. The first one is, for space, our options are really limited in our ability to get up there. In the top left, there are concepts such as stairs or vertical ladders up into space. If you throw a rock out past Geo on a long string, so strong, 10 times stronger than anything we've been able to build on this Earth to date, that potentially you could just climb up the ladder and access space that way. On the top right, you've got things like circular sleds spinning around. And in the bottom left, this is one company that is looking at spin launch in the US. It's looking at spinning things in a vacuum and then shooting them out at max speeds in order to get them into orbit. Center bottom, you've got things like sleds accelerating with rocket powered. And then in the bottom right, cannons and artillery. So the US Army trialed things to get up into space. They reached about 40 kilometers, but the trick there is you also hit about 20,000 G, which isn't good if you're a warm, squishy thing like a human, but potentially okay for electronics. So getting to space, we're really stuck with the age-old problem. In order to get up, you have to throw stuff out the back, and that's a momentum transfer. And for space, the problem is getting the rocket up there without blowing up. If you just to make some comparisons between a 747 and the space shuttle when it was operating, the thrust is an order of magnitude higher. The fuel burn, we're talking about 4 tons of fuel a second being converted into gas. And so just think of that every second, that liquid turning into gas, thousands of times more expansive and potentially disrupting your spacecraft in an explosion. And all in order to get to 8 kilometers per second. For those of you who haven't done physics in a while, the idea is the Earth is round. If you throw an object towards the Earth, it will fall and hit the Earth. If you throw it fast enough, it will fall to the Earth at the same rate that the Earth falls away. And that speed equates to about 7.6 kilometers per second. And that's what we call orbital velocity. If you hit that speed, then you'll never hit the Earth because your forces are balanced. Your centripetal force is balanced by your inertial force, and you'll continue to spin around the Earth. Now, you can't do that at low level, but if you get up high, that's important. So you look at a spacecraft trying to get up to orbit in about 5 to 6 minutes, about 300 seconds. It's got to get to 8 kilometers per second. Simple maths just shows that acceleration is velocity over time. You're talking about 2.6 Earth gravity of acceleration. So that object has to accelerate 2.5 times the acceleration rate that just the Earth falling to the Earth provides for a good 5 or 6 minutes. That's really hard. And you've got to do that without blowing up, all in order to get orbit. So that's the first problem about space. Really hard to get there. And this is still the only way that we've got of getting up into space. The second problem is relating to momentum as well. Moving in space is difficult. Efficiency on the Earth is quite simple. You push against the Earth pushes back and you go forward. Very efficient. Ships move water through the screws and the propellers that they have, and they shove tons of water, accelerate through that propeller, and they're buoyant as well, so they get some efficiencies there, and they move cargo around the world very effectively and cheaply. Aircraft are less efficient, but they move in the same manner. They squash and suck in tons of oxygen and air. They add fuel to it, they light it, and then they accelerate it out the back in order to go forward. The problem there being they need to maintain forward velocity to keep getting that air. Now in space, there is nothing to push, pull, throw, or grab against. And so for every action that you want to create, you need the reaction, which is to throw something out the back. And so to get to space, it's difficult. You're already burning tons of fuel to get there. And then once you're up there, you need tons of matter if you wish to maneuver around. And so that's another problem with space. It's a very physics-driven field. Pure physics applies, orbital dynamics, and it's very inefficient. If you were to make an analogy, excuse me, if you were to try and drive between 2 capital cities in Australia, for example, Canberra and Sydney, and you were to use it by throwing water out the back of your car on very efficient wheels, you would use up about a swimming pool's worth, an Olympic swimming pool's worth of momentum. Conversely, you could just carry a tank of gas, 50 liters, and you'd get there no problems. So efficiency from a pure momentum transfer perspective is very poor. Keep having trouble with my mouse. I threw this one in for the engineers amongst us. And so this is just an efficiency chart. It's a specific impulse on the y-axis. On the x-axis is your speed, and it just shows that speed going out to about Mach 10, which is what you want to get to for your spacecraft. Now, the problem here is if you look at the graph, you can see that turbofans, turbojets, ramjets, etc., are all increasingly less efficient. They move down the specific impulse line, but the only thing that can get you up to Mach 10 is a rocket. So we're sort of stuck with an inefficient mode of getting up there as well. Now, another thing about space, things move strangely. I'm not going to go into all of these laws, but Kepler's second law is particularly important. It talks about the motion around objects being elliptical, and also he defined a rule where he said the area circumscribed by the arc over a certain time is the same. But what it means is that as you get closer to an object, like the sun or the moon to the Earth, or a satellite, then you're going to accelerate. You're going to move faster. And then as you go up higher, you're going to slow down. And I'll show that in the next slide as well. And the third thing here is the angular momentum is constant. So your rock whizzing around on a string around the Earth is moving at very high speed. It actually takes a lot of energy to change your twist in orbit. So it's quite different from changing the dimensions of your orbit, just moving in and out. You can do that by changing your velocity. But if you want to twist in orbit, change potentially like 60 degrees, again, it costs you a lot of energy. So often people say, why don't we just maneuver the satellite, change its plane? Because it was probably simpler to get the satellite in the right plane from launch than it is to try and maneuver it in orbit after it's already got there. You now no longer have the fuel and you don't have the engines to maneuver it. And as an example, the space shuttle, when it was in orbit at sort of 300 kilometers up with the International Space Station, if it used all of its remaining fuel to try and change its twist, it would get about 6 degrees. That's not much considering it had quite a bit of fuel up there. Now, I mentioned this concept of energy. Again, if there's no friction up in space because there's no air or atmosphere to pull you back, then your energy is going to be relatively constant as you maneuver around. And so what happens is, as you accelerate around the Earth, if you come to the bottom, it's just like falling down on a swing or down a slide. You accelerate towards gravity pulls you down, and you get a kick around the Earth, and then you climb back up. And as you climb back up, you slow down, your kinetic energy goes down, your potential energy goes up, but the total energy is the same, and you maintain that momentum and that orbit forever. Now, another aspect of space, and we could go on for quite a while here, but it's a really menacing environment. We take for granted the Earth, it has this beautiful magnetic core, this iron core that provides a magnetic field, and it basically keeps all life on Earth here. Without it, high energy protons and galactic radiation, ionizing radiation at very high energy levels in terms of electron volts would come through and disrupt our DNA, shred DNA. And what happens with spacecraft is that they now operate up through these regions where you can see on the north and the south, you've got the poles, and that coalesces all of this high energy matter. For the north, those in Canada, they'll see the aurora borealis, the northern lights, and in the south, if you're down near Antarctica, you see the aurora australis. So all of that high energy particulate matter being funneled up through the north and south. Now, the problem here is that spacecraft may pass through these choke points of matter, and there are known hotspots around the Earth that can cause chips to flip, ones and zeros to lose track, and in fact burn out circuits. Not only that, that ionizing radiation is attaching itself to spacecraft, and unlike Earth, you can't touch something in order to discharge your static charge. You've also got other problems. Heat. In Earth, you can lose heat in 3 ways. You can touch something and conduct it. You can blow a fan over yourself and convect it away, or you can radiate it out if you want to go out and sit under a tree that's cold or absorb sunlight. But in space, there's only one way to get rid of heat, and that is to radiate it outwards. And so now you have the problem. If you look at this picture, if you're on the hot side of the sun, you're potentially 250 degrees centigrade. The cold side of your spacecraft might be minus 250 degrees. How do you transfer that hot side to the cold side in order to radiate it out into cold space? You don't have pumps because liquids don't work. Liquids don't flow properly. You may need to wick things or conduct things through metals. And so getting rid of heat and shedding things in space in terms of energy is another difficult problem. And so for a lot of our CubeSats, the problem is they're so small and powerful that shedding heat becomes their limiting factor. It's not actually the power that they can deliver. It's how fast you can get rid of heat. Other things about the menacing environment, it's a vacuum, so no air, but that means that metals can get very close to each other. We typically have on the Earth air between particles or matter as they squash down. You may not see it, but there's definitely an atomic layer there. But in space, you don't have that cushion. And so metals can actually touch together at the atomic level, at the van der Waals force level, and effectively vacuum well. You'll never get them unstuck. So if you design your spacecraft poorly, you design an airlock that doesn't take this into account, you can potentially leave your astronauts outside. And the other problem is, for many of these older spacecraft that were $1 billion to put up into geostationary orbit, they're going to be up there for 10 to 14 years, and you can't service them. We're still having trouble servicing spacecraft, even to refuel. And so design something that's going to live in that horrendously harsh environment and make it last for 14 years. So again, old space, the space that we've known for 50 years, has been typified by very precise and bespoke engineering in order to get these spacecraft to last that long. And if you've ever been on a space production line, such as I've seen with, say, Boeing, you'll see lots of people carrying small screwdrivers, still tying down little tabs and gluing things on, much like you would expect to see with a Rolls-Royce. This is not production technology. So where do we go from here? So another problem for space is we often forget this, but we are fixed to Mother Earth. And so space has terrestrial roots. If you want to get up into space, we have a number of launch sites around the Earth, but there's a couple of sweet spots. If you're sticking near the equator, then the Earth is spinning east, well, I won't talk about clockwise, but the equator is rotating towards the east. And if you want to go out to geostationary orbit, then you can get a 15% saving in fuel by getting a kick off the equator and pushing yourself up to geostationary orbit. Similarly, if you want to fire north or south and you don't want to go over land, then ideally you're going to have to fly over water. And so great for the US, you've got the two classical sites of Cape Canaveral, which is the site of the Apollo missions. Out to the west of the US, Vandenberg, which is where the US does national security payloads, and SpaceX is doing some launches into low Earth orbit. But looking around the globe, real estate is tight. For Russia, they have to fire over land, and they've had rockets fall into land, boosters, and kill people. And for China, their most recent site is Hainan Island, about 26 degrees north, in order to get that kick up into space and deliver a bigger payload, so up into the sort of 80-ton class. For Australia, what we're looking at is a launch site in the north, potentially from Northern Territory, to access that equatorial orbit or around the equator I mentioned. And then for Adelaide or South Australia, we're trying to build a site out at Whalers Way, which is west of Adelaide, and launch out over the poles. And so for that, you can get some polar orbits coalescing around the poles, very rapid revisit over the Earth, and potentially sun-synchronous orbits too, where you pass over the Earth at the same time every day, which is great if you're trying to do change detection and look at trees growing or buildings being created. But yeah, you can see they're limited spots, and as we move into a new phase of geopolitical tensions, a lot of these sites are at risk from adversaries or threats, be it cyber or conventional threats such as ballistic missiles. Now we get into this issue of perpetual motion. If you are up out of the atmospheric field, all of these objects whizzing around in space are going to be up there for a long time, even in low Earth orbit, potentially 5 years, up at around 500 kilometers. But moving to 3,000 kilometers, you might be up there for 100 years. So there's a lot of junk up there, stuff from the 60s, dead satellites, rocket bodies, bits of paint, slag from rocket motors, explosive bolts, astronauts' gloves, toolkit got lost. So this stuff is all whizzing around at 26,000 kilometers. And if you look at the top right, just showing you what a 1.7 gram of aluminium can do into a billet of heavy metal. And the space shuttle was reportedly getting hit several times in its windscreens towards the end of its career. And so many tens of thousands of objects in space, and more that is untracked. And so that's one of the defining problems, or the quintessential problems of new space, is how do we manage this domain as we potentially fill it up with debris. And this is just one case study showing you what happened in 2007 with an Iridium live satellite and a Cosmos, a defunct satellite, a Russian satellite, and these two satellites collided. The only thing I wanted to show you here mainly is that it generates a lot of debris. And the analogy when you're hitting objects at 8 kilometers a second is that you don't bounce off each other or hit each other like you would on Earth. It's more like two fluids, streams passing through each other. So there's this sort of meshing and interaction, and you slightly disrupt yourself, but then you cascade out the other side. Now, all of those red dots, some of them will burn back into the Earth, but a lot of them are still up there. It'll take 30 to 40 years before they all come back. And so any one of those potentially could hit the International Space Station or another one of your satellites. And the green dots shows you everything else that's being tracked up there. So thousands and thousands of objects being tracked every day by countries like Europe and Germany and China in order to understand, what this potential threatening debris field is like, but also to do traffic management and make sure that they can deconflict if possible. So another problem to do with space. Now, this is a similar graph just showing you where the debris is growing over the years. It's still it's fairly old, this slide, but it just shows you that with the Chinese ASAT test, the Iridium Cosmos collision, we've had recent near misses. My point here is not to focus on the number of objects, but to me, this is quite scary because it represents exponential growth. And Kessler, who is a NASA scientist, postulated that at some point in space, we could have a cascading debris field. One object hits another, which hits two, which hits four, etc., and potentially destroy a shell in orbit. And his projections back then have been updated with the number of satellites now going into orbit, like Elon Musk is proposing to put 5,000 to 10,000 satellites into low Earth orbit. And so the potential for a cascading debris field is increasing. And we're talking about numbers in the millions, 1 in a million, which if you're a, excuse me, if you're a, excuse me, if you're a mathematician, you'll understand that it's not that unlikely. Sorry. Oops, sorry again. Okay, so I'm just going to quickly describe 3 of the orbits. So we have this low Earth orbit, again, very close to the Earth in terms of that map. But you can just see the ground trace there in the bottom right. As satellites pass through the Earth is moving 15 degrees an hour underneath. And so the satellite is effectively looking like it's moving westward as it retraces the Earth. So the problem here is if you want to capture a lot of the Earth with low Earth orbit satellites, you need a lot of them in a constellation in order to fill that shell. I mentioned MEO, the medium Earth orbit. This is anywhere from 5,000 to sort of geostationary orbit, but we've got a lot of satellites out there doing GPS. And the problem here, you look 20,000 kilometers away. So that GPS signal, which is the equivalent of a 40-watt light bulb at 20,000 kilometers, sending its signal back to Earth and being picked up below the noise floor here. So these signals are very, very weak and they can be jammed. And then geostationary orbit, this is the sweet spot for what is considered a lot of classic space. This is where your cable television companies in the US or your satellite TV companies in Australia, like Foxtel, put a satellite out there and you get this magic point as you move away from the Earth, you slow down, but at a certain distance, your speed around the equator matches the Earth's rotation exactly. And so if you are in that sweet spot, you will, to all intents and purposes, from the Earth, appear as if you're hanging in the sky around the equator at that point forever. Now, these satellites do spend a bit of fuel to jostle and maneuver and maintain their station, but this is valuable real estate. From that vantage, you can see a lot of the Earth, and this is where a lot of your weather satellites are. But the problem is you're still a long way away. And so communications need to be powerful. Hence, you see large satellite dishes on the ground, 10, 20-meter dishes. And you also see large optics out in space for these satellites. So we're talking very large satellites, 10 to 20 tons, something like a double-decker bus sitting out in geostationary orbit, flying all that way out there, is quite vulnerable because that geostationary belt is also being filled with debris and potential problems. We have this unique orbit called a Molniya, or a highly elliptical orbit. And I won't go through the physics of this. I mentioned before, you slow down as you go high, but what effectively happens is that it looks like you hang over the Earth at a very high altitude. And we're talking 100,000 kilometers up in space. And interestingly, for this altitude, in this orbit, it's been optimized for both hang time over the US and also Russia. So this is where you find a lot of your early warning satellites. And then finally, just to put it in all perspective, this is the Earth here, I've showed you before, the blue zone, low Earth orbit, and then all the way out to the red zone, which is geostationary orbit. If you look at the very bottom left, that small Earth, it just shows you with perspective how far the moon is out. And so one of the interesting things about space dynamics, momentum, is it costs you a lot of energy to get up out of the gravity well into, say, geostationary orbit, but it doesn't take you that much more to get to, say, the moon. Now, geopolitics has a place in space. I've mentioned that you can see things out to geostationary orbits, so terra firma has an importance, and so if you can see objects, they can see you. So similarly, watching and observing things in space, either for communications or just for domain awareness, is important. Interestingly, the legal framework for space is weak. 1967's Outer Space Treaty should tell you everything you need to know, because the date is quite a long time ago. And so what we have here is a legal regime that really says three main things: return astronauts if they land on your soil, don't put weapons of mass destruction up into space, and apply through the UN for various spectrum licensing issues. So it's a fairly weak legal regime, so ripe for new space lawyers who want to get into that area. And space is a commons, and like all commons, we suffer from the same problems: human rights, oceans, water, climate change, etc. Like all commons, it can be destroyed through the thoughtless actions of any entity actor. And finally, it's just becoming very crowded. And so we're dealing with that now today, but because it is a commons, no one owns it. How do you deconflict all of those objects? And so finally, I just want to go through just a couple of slides about what are some of the challenges and opportunities for Australia and the world. So we have many nations now moving into space, many disruptors. So 70 nations have launched into space. Many companies are being formed and evolve as we speak. So there's plenty happening up there. What does that mean? Well, it's a concept of new space. So we're going away from large, bespoke, billion-dollar systems. They're still required. But if you look at the new space market, we're talking about taking advantages of additive manufacturing, high technology, battery size reductions, chips, small electro-optic sensors, and cramming them all into small satellites. We call these small sats typically below 500 kilometers wet mass, 500 kilograms wet mass, but you get pico, nano, it doesn't really matter. We're talking about things that are very small, about the size of a bread cube, or if you look at the bottom left, a 1U satellite, 10 by 10 by 10 centimeters, and throwing thousands of these things up there. So many, meshed and networked. The bottom right just shows you one older vision of what Elon Musk is hoping to do with his Starlink constellation. So thousands of satellites up there, all talking to each other, delivering internet to the globe. And disruptive technology is afoot. We have 3D printing, carbon windings, video in space, and some of these smaller satellites are just getting phenomenal capability. Now, what does it mean from a market perspective? Well, the global market is estimated at about $360 billion still this year, expecting to grow to about $1 trillion in the next 10 years to 2030, which is phenomenal growth. That's about 7 to 8% compounded growth, still largely dominated by either large nations, governments, and also the services they provide through communications and ground stations. But there is a new market that's emerging, and that's the one that is really exciting for people moving into new space. And where does Australia want to go? Well, the Australian Space Agency has a goal to triple its jobs, going from 10,000 jobs to 30,000 jobs over the next 10 years, and take the revenue from 4 billion to about 12 billion. So again, tripling. That represents a very aspirational 8% growth, 8.4% growth over the next 10 years, but we have achieved 8% growth over the last 5 years. And this is typical of the space market. The UK, for example, set out about 10 years ago to capture 10% of the global market. They've now got about 5% of the global market and expanding at about 3.5% per year. So quite good growth if you're looking at this new sector. So with that, I'm going to end it here and just certainly open it up to questions for Megan, as I haven't been able to see what's been happening behind the scenes.
Thank you so much, Darin. We have a few questions coming in, but just a reminder, guys, you can submit them now. Darin has many skills and many backgrounds in this domain. So if you've got any question, be it about technology, about the uses of space from a commercial perspective, about how government can approach it, or even about the space policies that are existing today, feel free to post them in the chat. Now, I'll get started with a question. There was a little bit of preamble to this question, but it came down to, in terms of a roadmap moving forward for both Australia and the more global space industry, how much do you expect history to repeat itself? Think. Person was speculating that certain elements of what happened during the space race are playing out again now with sudden technology leaps, etc.
Yeah, good question. Absolutely. We are terrible as humans. We are still a globe that is built up of nation states, and nations are very definitely focused on sovereignty and their own national security. So national security concerns still dominate space. And what we are seeing is, I guess, space going from what was largely the playground of superpowers like China, Russia, UK, US, and where there was an agreement to not really interfere with any other capabilities. With now the 70 nations in space and the proliferation of objects, we're now seeing things become quite complex. And because space law hasn't kept up and the rules of the road haven't developed like they have on 2,000 years of Earth history, in terms of if you look at maritime law, we are dealing with a very complex emerging domain. And not only that, I'm sure some of you are aware that the US has decided that space is now its newest force. So it had 4 forces: air, land, sea, and the Marine Corps, and now it has Space Force. And so what that means is the US will focus on that as a domain in and of itself, not just a domain that delivers services. The French are considering the same thing. China several years ago formed its Strategic Support Force, which also looks after space. And so we are seeing increasing tension in space.
Fantastic. We had another question in there, which was, how do you get rid of space debris? Can you?
Yeah, this is a really tricky one. You can, but the two main ways, you can either go up and grab something and push it somewhere else, or if you can slow things down to the point where they can then get closer to the Earth and deorbit by burning in, that's another way. If you want to do the deorbit problem, then you really have to do that fairly close to Earth, and they are talking about technologies like laser ablation, where you can hit something on the nose and it'll effectively provide a puff of gas which will decelerate the object. Very precise, very difficult. The other alternative, going up there and grabbing stuff, I mentioned to you the problem of space dynamics, momentum. It's going to cost you a lot of energy and a lot of mass to go up and grab a little bit of mass and a little bit of energy. So you're dealing with those same problems. It's very expensive, very difficult. This is not a simple equation of just moving around like we can on the Earth. It's, I think, at this stage, technologically impossible. And I think we're going to be dealing with this problem for many, many years to go.
Fantastic. We have a space policy question in here, which is, do you think we should be trying to update our international treaties? And if so, what should be the priorities?
Yeah, if you're a constructivist and believe the world can be shaped in the way you wish to see it, then I would say, yeah, go all out for treaties and try and develop them. But if you're a realist, you might subscribe to the point of view that law really only happens when you have calamity or problems, especially international law. And so my fear is that we can develop a lot of law in the potential that we need to do something, but I don't think nations are going to follow international law in space, or the law that's developed, until we do have problems. And if I can just give one analogy, you look at the way the Chicago Convention defined air travel in the 40s and 60s, there was a corresponding interest for countries to share goods over air. And so the rules said that if you want to fly in my airspace, you'll follow my rules. You'll speak in English, you'll talk about feet for altimetry, and you'll use the similar radios. But for space, there's no real driver. There's nothing driving Australia to follow US law or Russia to follow Australian law if overflight is already guaranteed. So I do believe that law is problematic for space. But if we are going to develop treaties and issues, then I would say one of the first problems is to talk about norms. Australia is a great player in that area. Establish norms of good behaviour and try not to muck it up with too much debris. So yeah, don't go crazy up there.
I have a question about, I guess, career advice to a certain extent. Do you have any advice for students who come from backgrounds that aren't traditional STEM, who want to get a start in space, as a lot of the jobs seem to be still yet to be made?
Yeah, my advice is be good at whatever it is that you want to do. Space captures a certain interest, and certainly people who want to get into space usually are quite motivated to do what they can. It is STEM heavy, but interestingly, the #1 job, according to a recent UK report that's required for space, is software engineering. Now, some might argue that software engineering isn't real engineering because you're not actually making things, but software is driving a lot of space technology. And similarly, in other areas, space law, we're working on a program in South Australia to do space farming, so biology. How do you produce food in a very austere, harsh environment and recycle all of your nutrients and get rid of waste? Lawyers, ethicists, architecture. So if we're looking at moon to Mars and putting structures on the moon, how do you take moon regolith, for example, which is quite a coarse and abrasive sand-like substance? It'll shred normal materials like Kevlar. How do you build objects out of that? How do you make bricks out of it? Do you dig a hole and cave it in? So there are a lot of fields that need to be developed, including those other areas of how do you apply the technology, especially in software, because we don't know what to do with the petabytes of information that's coming from space. And so if you can make use of that in novel ways, then that's another career in the offing.
Speaking of kind of, I guess, intersections of disciplines in space, someone is asking about whether or not there is an intersection between medical science and space, and I think it's fairly clear that there is. But they're also asking, how do you expect that the space industry will invest in the progression of biomedical research in space?
Yeah, biomedicine's an interesting one. As we do talk about Moon and Mars, I mentioned the radiation problem. We often don't tell aspiring astronauts who want to go to the Mars that it's a death mission, because your DNA will be shredded and you will get cancer. So we need to solve that problem. You can shield humans, but there are also other ways to protect tissue that are being investigated with different fluids, different diets. And in fact, we have someone in South Australia who did a conventional medical degree, and her parents told her not to get involved in space, but she's somehow found a way there. She's doing her honours studying the loss of muscle tissue in the gluteus maximus, so studying butts in space, using data collected through Germany. But again, she's found her niche in space, doing space medicine there, and getting a lot of help. We've introduced her to people, and she's found her own mentors, but she's got astronauts in the US helping her. And so, yeah, you can make a career out of certainly these areas, and it's still a field ripe for the specialization.
Something on, I guess, the more, we've got a STEM side here, which is, what AI/machine learning developments are you tracking that could be game changers in space?
I wish I was tracking more. So if we're to talk about the potential for space, really, I believe this is the large untapped area. So the petabytes of information being delivered, we still have a world where the great powers have used the most of the intelligence derived from space in terms of foreign intelligence and tracking what's happening in other people's countries. But now you have, for example, the large incumbents like DigiGlobe producing 0.4 centimeter resolution, so being able to see ahead from space. They're now delivering so much information, they don't know what to do with it. You take into account video information and multispectral, so the ability to grab not only what our eyes see, like red, green, blue, but fuse it with, say, infrared, ultraviolet, a couple of other different spectrums, split it into hundreds of chunks, weave that all together. Everything on this Earth has a unique characteristic or spectral signature. And so you can identify things from space like plants, concrete, fire, cloud, smoke, that you can't do with just normal vision. So all of that information is rich. And so we're still defining ways about how to use that. And that's where machine learning can come in. So getting machines to take out the drudgery of looking at objects and just siphoning it off and collectively saying, what I would like to see is Farmer Joe says, I want to know when to water my crop. And he doesn't care how space services work. He just pays his money down through a credit card, or the state delivers it. And it tells him your crops are going dry or you've got a weed. And that's what we want, ubiquitous applications of space technology, all through AI and ML.
Again, a slightly different perspective, really fantastic diversity of questions here. So thank you to the audience. I think that space is the most inspiring frontier that puts our delicate existence into perspective. What do you think it will take for people to care about space as it is without incentives of war or money?
Yeah, it's a hard one. The first astronauts, when they looked back to the Earth from the moon, saw this blue jewel, and astronauts often will talk about the impact it had on them to sort of suddenly put in close or stark relief that the Earth is this fragile, ball of matter and gas. Looking up, one of the problems we have with space, and this is mentioned by quite a few space strategists, is that it's out of mind, out of sight. You can't really see it or picture it. It's just up there. So it's very hard to put it into that perspective where you suddenly take a very close and abiding interest. We're far more worried about our credit cards being hacked or our computers. And so if you look at how cyber has developed, they've really been able to articulate their issues, gain money and support and government legislation in order to reform the way cyber transactions are conducted around the world. We've only had computers for 20 to 30 years. So space, it's been around for 50 years. We're still dealing with this problem of how do we capture that? I think it's a very difficult problem. And so programs like Moon to Mars should help. But it's a difficult one.
I've got a couple more questions and I'm going to let Darin answer them in just a second. But before he does, I just wanted to make a quick announcement on the Astra end. So obviously the Astra program is in its early stages, and we've been posting a lot on social media about what we have up and coming, but I just wanted to make an important and quick announcement, which is that our applications to join the program are actually now open. They'll be up on the website now, and so if you go on there, you'll be able to see details about the topic that we are doing, which is igniting an industry, creating a blueprint for launch in Australia. It's going to be really exciting. We've got some fantastic people on board, including Gilmore Space Technologies, which is going to be great. And you just have to fill out a quick application, and we're hoping to have the program starting in early December. So check that out. Otherwise, we'll come back to questions. Darin, can you hang on for a little bit longer and
it's good. I don't know what time zone everybody else has, but it's fine.
Fantastic. All right, we've got a question here about legislation again. So what are your thoughts on current legal regulations in place, given that they seem unenforceable? What do you think, how could we promote greater cooperation in space between nation states and private organizations?
I think a couple of things. International theory of politics will tell you that the greater interaction you have with other nations, that can promote good behavior. So if you look at the US and China, that was once touted as an example where the trade between US and China was a positive thing because it forced them to both be reliant upon each other. but then you can get a president who decides to go a different path and turn that into a negative. So it's really difficult. Internationally, I think coalitions that are willing, so constructivism and liberalism is important. So building norms through entities like the United Nations, if countries agree and abide by the rules, and most importantly, enshrine those rules in their own national law, then that's one way to get good outcomes in space. But if you've been following it, many of the initiatives that have been tried have failed, and so space is still largely unkempt.
All right, and we've got a question about Australia's role in space. Do you think Australia needs to have a niche in space? And if so, what do you think it should be?
Yes, I would say absolutely yes. You don't want to do everything. But we've identified for South Australia, for example, that it's important to do the full value chain. I mentioned that earlier, if we want to be competitive, but noting that launch is only 2% of the global market, with over 100 new launch providers vying for some of that territory. It's quite competitive. Sorry, you were asking about where Australia should niche. Yeah, look, I think we need a national strategy around both defence and civil matters for space. It's no point trying to keep the two separate. And if we're looking at things for Australia, I think it needs sovereign capability for its own spacecraft. And that would mean launching them from both the north and the south into different orbits, equatorial and polar. I would argue that we need to be able to design, manufacture, and launch satellites from Australia for its own sovereign capabilities. Other areas for Australia, we are very good at machine learning. We have some fantastic technology in photonics and the processing of data. And so there are various niches there. Australia exports a lot of its technology. We're very high internationally in terms of development of IP, but we're very low in terms of entrepreneurship. And so I see space emerging as a new field where niche players can be entrepreneurs and can disrupt old space. We're playing against the incumbents, people like Boeing and Airbus. They're finding it a real struggle to crack this new market because they've got billions of dollars and 50 years sunk into existing infrastructure. And so it's very hard for them to pivot to new space. So that's the opportunity we all have as young nations.
Just received a message saying, speaking of kind of Australia's ability, do you have any impressions on particular fields that might be suited to Tasmania? It's not often one of the areas that we discuss. It's quite often centred around South Australia and Queensland. So do you think there's any role Tasmania can play in Australia's space race?
Yeah, Tasmania's already doing a bit in terms of space domain awareness and tracking. I would say they would be a natural competitor to South Australia for polar launch. I hope we get there before you, because we only need one really. But you've got great access to the south, and if you look south from Australia, there isn't much until you hit Antarctica. So that's great real estate to fly and launch rockets over. And other than that, I think just some of these AI technologies. If you're looking for apps, so an example I've heard from a US company that's trying to make space capabilities ubiquitous, developing an app so that you can provide your credit card details and say, for example, tell me when my car park is filled, or tell me when a car park has got a car in it. And just doing that sort of information, that information is available. So the application of those technologies can be done anywhere. Upstream is difficult if you want to get into manufacture, but downstream, there's a huge potential there.
Questions about Australia's, I guess, goals as well. We've got people asking about whether or not Australia has goals beyond commercial motives, such as astronaut programs or exploration of planets. Yeah, really not my specialty, but the space agency, I guess it's become quite the general trend is if you have a space agency, then you might have a space program that lends itself to astronauts. And so Europe, for example, Andy Thomas, Australia's only astronaut, really had to become an American citizen to become an astronaut. But I do hope
with the formation of the Space Agency 2 years ago, that we will see an Australian astronaut up there. Now, I'm not totally a fan of human spaceflight because it's very expensive, very difficult, and I don't think we should be doing it alone. We don't need the prestige of a human spaceflight program, but certainly if we're partnered with, say, NASA or JAXA or the Europeans to offer a bespoke technology, and that gets us a shot at an astronaut, then one of you out there in Astra one day could potentially be that person, because it takes, you know, a good 15 years to do the training for an astronaut. My experience in the US, and I've met quite a few astronauts over there. I spent 7 years working in the US in DoD, and often if they're military, they'll come up through a flight test program, so they'll become test pilots, and then they'll stream some of those off into the astronaut program. So you had ex-heads of NASA being astronauts, and people like that. Pamela Melroy, who's been in Australia quite a bit, as an ex-test pilot, Fleet C-17s, is now back in the US. That's one way, but also if you have a civil space program like the Canadians do, they get astronauts up that way. So yeah, I'd hope to see an astronaut 10 to 15 years.
All right, I think we might finish up with one last question on space mining, which is just, what are your thoughts on space mining and Australia getting into it as well?
Yeah, it's an interesting one. I think it poses two issues. One is the legal aspects of space mining, and the other one is the resource potential. Australia did sign the Moon Accord, which says that we're not supposed to mine the moon, or that we don't own the moon. We don't own geography on the moon. But we have also signed up to Artemis, which is looking at using the moon's resources in order to provide life on the moon, using, you know, extracting water for fuel, for example, and to drink. But in terms of resource mining, if you look at asteroids, is the often quoted example. You know, a large asteroid 20 kilometers in space could have, you know, millions of kilograms of platinum and other rare resources and minerals, because these all stem from stars and they've all coalesced out in space and smashed together, and you get this nice rich environment to go and mine. So with robotics, you know, sending robots out to extract materials and bring it back to Earth, that's potentially very lucrative. We've got Hayabusa returning to Australia on the 5th of December, and I'm hoping to be out at Woomera to watch that burn in again. I was there for the last one in 2010 as it burnt in, so it's gone out to touch an asteroid, bring back some material, and return it to the Earth. But again, it's a difficult proposition, but it's certainly offering a lot of market potential, commercial potential. But yeah, you've got the issues of who owns it, where does it go? And the one thing you don't want to do is lug a 20 million kilogram asteroid back into the Earth's field and misjudge your orbit, and then have it slam into us and create another dinosaur dark age.
Yeah, I don't think anyone wants that.
Yeah.
Fantastic.
Oh, there's a quick question about Woomera. The best place to watch the re-entry will be from Kuba Pedy, not Woomera itself, because it's going to burn in several hundred kilometers up to the northwest at about 2 to 3 a.m. on the Sunday morning, I think it is, yeah. But I don't know how you're going to get up there and do that. That's a long way away. It's a good 8-hour drive. Oh, 5th of December, it burns in, but it's going to be at 3 a.m. in the morning on the 6th.
That's the JAXA mission?
Yeah, okay. And I don't have the exact numbers. I don't even know if they're going to promulgate that. They might, I think, yeah. We currently have 80 JAXA personnel in South Australia. They've all come here and under quarantine right now, and they're all getting set up to come out of quarantine and go up to Woomera in the next week or two. So it's pretty cool.
Exciting. All right, well, thank you so much,